Getting close to the end. Lesson 45 is fission and fusion. Fission is breaking apart. Fusion is putting together, in simple terms. And of course, when we refer to fission and fusion, we're talking about the nucleus. So in fission, the nucleus is breaking apart, and in fusion, nuclei are joining together to form one nuclei. And fission and fusion are the sources of enormous amounts of energy that we call nuclear energy because they are from the nucleus. Fission is responsible for all the nuclear power we have on Earth and is responsible for hydrogen bombs and atom bombs and all kinds of destruction and all kinds of good things that come with energy production, but it has some nasty byproducts, so it's not the greatest solution to our energy problem. Fusion is the solution to our energy problem if we can ever get that far technologically, because fusion yields a huge amount of energy with a very small amount of matter, and it is essentially clean. Anyway, before we continue, you should go to YouTube and watch, this, you should watch a video on fission and fusion. This is a pretty good one by Cassiopeia. There's lots of good videos on fission and fusion, but watch this one, I like it. And then come back to the video. So now that you watched the video, we'll talk about fission first, and then we'll talk about fusion. Fission happens with very big atoms, because very big atoms are, as we know, the nucleus is less stable because the strong nuclear force does not act. If you've got a proton on one side of the nucleus and a proton on another side of the nucleus, the strong nuclear force does not act. So big nuclei are more unstable, and they're more likely to fission, to split into smaller atoms that are therefore more stable. So it says fission, the process of causing large atoms with an atomic number greater than 120 to split into smaller nuclei. Sorry, atomic mass, I meant, not atomic number. Releasing energy in the process. It can start when a large nuclei absorbs a neutron, causing it to become unstable to the point that it falls apart. So we'll just skip over here. So here's your prime example of fission is a uranium. Uranium-235, uranium has 92 protons, becomes very unstable if you introduce this 10N. Obviously, that's a neutron, right? And just to review these numbers, the 0 is the number of protons, the 1 is the number of nucleons, and therefore this has one neutron because it has no protons but one nucleon, so it must be one neutron. So that's the terminology for one neutron. So you take uranium-235, you add a neutron to it, and all of a sudden it becomes uranium-236, and at that point it becomes very unstable. So you just add that one little neutron, and all of a sudden, oh, all hell breaks loose, excuse my language. And it will split. It will split into barium and krypton, or strontium and xenon. Could go either way. Plus, it will then also release 3 of those neutrons right here. So it releases 3 extra neutrons. And what do those neutrons do? Well, they go out seeking other atoms of uranium-235, changing them into uranium-236, which then fission, break down into smaller particles, and then so now you've got all of a sudden nine neutrons, and they're going to go out and seek out 9 other uranium-235, and you can see what's going to happen here. This is called a chain reaction. It's an exponential growth, and a chain reaction is what is if it's uncontrolled, we can blow up things. Yay! No. If it's controlled, we can harness that energy and use it for good, for like nuclear reactors, power plants. Those are the good things of fission. The bad things are when we let the chain reaction just go unfettered and it explodes, and then we have Hiroshima and all kinds of ugly, bad things. Now, unfortunately, it's not all good news because nuclear power plants have burned down. Chernobyl, you should definitely watch a video on Chernobyl in the 80s, a Russian power plant that went critical, and the devastation from that was devastating, and people suffered for years and years because of the radioactive poison that came from that reaction. And then there was a more recent one, Fukushima. Blah, blah, blah. We're going to kind of skip all this because I've just discussed all this and I don't want to go into that much detail. Watch a video on the Fukushima disaster that was in Japan. And they had all kinds of safeties in place so that Chernobyl would never happen again in Fukushima, and still it went haywire and people lost their lives. And when nuclear reactors go bad, it's bad. There's bad and there's bad. A nuclear reactor going bad is bad. Okay, so that's fission. Now on to okay, wait a minute, what are we given here? So you can read over these notes. It talks about the problems with nuclear reactors and so on. So in a nuclear reactor, you start the fission process, but you slow it down so that it's controlled, and then you get the energy from the heated water or some kind of heated substance. You get energy from that, but you can control the reaction, and if you do that, then it's good. Okay, blah, 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 blah. And then you can read all that. You can read about the CANDU reactor, one of Canada's famous ones. Now we get on to fusion. And fusion is insanely cool because it's basically what's responsible for our sun and every star in the universe. So fusion is when at great temperatures and pressures, atoms fuse together, and the best example is our sun, which is, as you can see, presently 73% hydrogen and 27% helium. And as the sun burns, two hydrogen atoms get together, fuse into a helium atom. So as the sun is burning, it's just converting hydrogen into helium. At some point, the sun will become all helium. But probably long before that, the sun will exhaust all its fuel, and actually the sun will expand because the gravitational forces won't be able to hold it together. It will probably engulf the earth and so on. And we won't be around to witness that nasty day. But yeah, so this is what the sun is doing. It's presently fusing. So you have to have great temperature, great pressure enough that it can overcome the repulsion of nuclei, and it fuses them together. And we call this a proton-proton chain. And then there are all kinds of, now this is what happens in our sun. Deuterium, what's deuterium? Well, look what deuterium is. It's a it's a hydrogen atom with a neutron. So hydrogen usually is one proton with one electron, one proton, one electron. But if you stick a neutron in there too, it becomes deuterium. So this is normal hydrogen. This is deuterium. Totally makes sense. They both have one proton, but this one, so hydrogen 1 has one nucleon, which is the proton, but hydrogen 2, which we call deuterium, has a neutron and a proton. And his tritium, and tritium has 2 neutrons. And deuterium and tritium in the sun will get together and they will fuse, and now we have 2 protons fusing together to become helium. And in this case, in this picture, it looks like it's helium-5. Right? It's got 2 protons and 3 neutrons. And in that fusion, some energy is released. So now you've got, it fuses together and then it becomes helium. Like that's essentially an alpha particle. A helium atom can have neutrons, and this one neutron is released. And that thing there, energy, some energy is released. And in that, how much energy is released? Let's go, wait a minute, I have another thing here. Is this it? Do I have a Here we go. Deuterium and tritium fusion produce 17.59 mega electron volts of energy, which is not really a lot of energy, but that's one atom. That it was two atoms fusing to make that much energy. And in the sun, wait for it, where did I put it? In the sun, every second, here it comes, where is it? 600 million tons of hydrogen are converted into 596 million tons of helium every second. Every second that happens in the sun. And our sun has been burning for about 4 billion. It was formed 4 billion years ago, and it's going to burn for another 4 or 5 billion more. So that just goes to point to the magnitude of what's happening here. 600 billion tons every second. Every second. And just remember, our sun is just a very average, even small star. Those big ones, I can't even imagine. Okay, so then there's some other type of reactions here. Actually, let's go to this page here. So there's here's a deuterium fusion, right? Where two deuterium atoms get together and again produce helium-3. Here is, they can also produce, this one produces helium-3 and a neutron. They can also produce hydrogen-3, hydrogen-1, and some energy. And so there's different combinations of fusion that you can have. In our sun, we focus on this one, the deuterium-tritium fusion. And if you've watched Spider-Man 2, you should watch Spider-Man 2 just because of this concept here, not because, well, I enjoyed it. Spider-Man 2 is good because in Spider-Man 2, they are trying to create fusion on Earth. If somebody can learn to create a fusion reaction on Earth and contain it, you will have such an incredible source of energy that will essentially solve all the world energy problems. Of course, it will probably create a whole bunch more, but you know, you could probably end starvation within a few years if somebody could figure out how to do this process on Earth, how to fuse things. But you need high temperature and high pressure, and what a lot of physicists and scientists are working on is what they call cold fusion, and cold fusion allows you to do it at temperatures that are less than 27 million degrees Kelvin or whatever. They're ridiculously high temperatures. But if you could learn to do it at, let's say, 1,000,000 degrees Celsius or 1,000, then you would you'd be onto something. All right, I think that's it. At this point, I'm just babbling. So just watch some videos on fission and fusion. It's good stuff.